Hello viewers, today we are going to discuss about engineering materials and the chapter is imperfection in solids. The brief outline of the talk is we will discuss different types of defect, then the description of point defects, what are the type of impurities for getting defects, composition of impurity in alloy, understanding of linear defects, interfacial defects. What is imperfection? Every solid has some amount of disorderness called imperfection. Now, imperfection gives very special physical and chemical properties to the solid. Now, crystalline defects are called lattice imperfection, which are of the order of atomic diameter, and imperfections in crystals are basically classified on the basis of dimensionality. So, the first type of defect is called point defect. These are present at different points in the crystal, and because they are 0 dimensional, that is why they are called point defects. Next, the defect is linear defects or dislocation, which are 1 dimensional defect, and the third one is interfacial or boundaries, which are 2 dimensional defects. Now, let us discuss the first defect, that is point defect. So, point defects are of two types. First one is vacancy, which is absence of lattice site due to variation of temperature. Now, if we want to find out the number of vacancies per cubic meter, then we can use the following formula, that is NV is equal to N exponential minus QV by KT, where N is total number of lattice point per cubic meter, QV is energy required for creating vacancy, and T is the temperature. So, as you can see on the left hand side of the slide, there is a dotted circle which represents the vacancy in the lattice. Now, the second point defects is called self interstitial. These are extra atom from lattice at the void in the lattice structure. In metal, usually we do not find self interstitial because the metallic atoms are so big that their presence in the voids disturb the surroundings of the lattice. That is why rarely we will find self interstitial in metallic lattice. As you can see in the figure on the left hand side, the dotted circle represents a self interstitial in the lattice. Now, what are the reasons for getting these defects? Basically, these are the impurities in the lattice structure which brings in the defects in the lattice. Now, alloy is also some sort of defect structure of a lattice, which is having some amount of impurity in the solid. Now, because of the impurity in the solid, the physical property of the solid changes drastically. So, addition of impurities in the solid causes a solution and or second phase in the solid. Now, this depends on the concentration of the impurity in the solid or the temperature of alloy. Sometimes the higher concentration material is called solvent and lower one is called solute. Now, in solid solution phase, the impurities do not change the crystal structure, and the impurity point defects are either substitutional or interstitial. As you can see in the figure in this particular slide, there are two different types of impurities shown. One is substitutional impurity, which is represented by the green ball, and the other one is interstitial impurity, which is represented by the orange ball. For substitutional impurities, following conditions must satisfy, that is, the atomic number of the impurity must match with the atomic number of the atom in the crystal lattice. Then the crystal structure of both impurity and the lattice must be same, electronegativity of both the materials must be same, and the valency of solvent must be higher than the valency of solute, because here the crystal lattice is the solvent phase and the impurity is the solute phase. So, we need to maintain a higher valency for the solvent. Now, to explain this by taking an example, we can understand it in a better way. If we take the example of the alloy nickel, which is having some amount of copper in it, then we can explain properties whether they are maintained in this alloy or not. So, copper is having atomic diameter of 0.128 nanometer, whereas nickel has a diameter of 0.125 nanometer, which is almost same. Now, both the crystal structure for both the atoms or the solids made out of this atom is same, that is FCC. The electronegativity for both the elements is 1.9 and 1.8 respectively. And if we think of the valency, then copper has a valency +1 and nickel has a valency +2. So, they constitute a very nice solution and solvent phase. So far we discussed about substitutional impurities. Now, if we think of interstitial impurities, they are basically the impurities which are present in the voids of the crystal. Now, for FCC and BCC lattice structures, these interstitials exist in two positions, that is either in octahedron position or in tetrahedron positions. Now, these two positions of the interstitials are distinguished by their coordination numbers. Now, if we take for example, the coordination number for both octahedron and tetrahedron interstitials, then for tetrahedral interstitial the coordination number is 4, whereas for octahedral the coordination number is 6. So, if we now consider the individual lattice structures, that is FCC, then we find that in FCC there are two octahedral regions where the interstitials can lie, and they can be represented in the following manner. That is, one octahedral site is located at 0, half, 1, and the other one is located at half, half, half. And if we look at the tetrahedral site, then there is only one tetrahedral side in FCC lattice structure for these interstitial, which is at 1/4, 3/4 and 1/4. Now, if we go to BCC structure, then it has only two sides, either octahedral or tetrahedral side, and the octahedral site is located at half, 1, 0, and tetrahedral site is located at 1, half and 1/4. So, these impurities, they distort the lattice, as most of them have larger size than the atoms in the lattice. As we discussed that the presence of interstitials in lattice structure distort the environment around the particular interstitials, and since here most of the interstitials are larger in size than the atoms in the lattice structure. So, we can expect that the crystal will get distorted. Now, if we want to find out what is the composition of the impurity in the lattice, then we can find it out in two ways. One is by finding out the weight percentage, and the second one is by finding out the atomic percentage. Now, what is weight percentage? It is an alloy where a particular amount of a given impurity is present in the total alloy. Now, if we mathematically represent that, then we can use the following formula. Now, if we have to find out the weight percentage of an element in a alloy of two elements, that is element 1 and element 2, and if we are interested to find out the weight percentage of element 1 in the alloy, then we can use the following formula, that is C1 is equal to M1 by M1 plus M2 into 100, where M1 and M2 are masses of element 1 and 2 respectively, and C1 gives the weight percentage for that particular element in the alloy. Now, as we discussed, we can also go for atomic percentage, and atomic percentage is defined in the following way, that is the mole of an element in total number of moles of elements. That is, if we have a composition of two elements, that is element 1 and element 2, and if we want to find out the atomic percentage of element 1, then we can use the following formula, that is C1 prime is equal to n m1 by n m1 plus n m2 into 100, where n m1 is the number of moles of element 1, which is represented as m1 by a1, where a1 is the atomic mass of element 1. Now, at times we may need to have the weight percentage to be converted to atomic percentage or vice versa. So, in that case, if we have all the quantities which can be utilized to convert one form to other, then we can use the following formula to do the interconversion. For example, if we want to find out the atomic percentage of element 1 and we know the weight percentage of element 1 and element 2, then we can use the formula, that is C1 prime is equal to C1 A2 by C1 A2 plus C2 A1 into 100, or C2 prime is equal to C2 A1 by C1 A2 plus C2 A1 into 100. This is the conversion in which we get the atomic percentage if we have the weight percentage of the elements in the alloy. Similarly, we can find out the weight percentage if we know the atomic percentage of the elements in the alloy, that is by following the following formula, which is represented by C1 is equal to C1 A1 by C1 A1 plus C2 A2 into 100, and C2 is equal to C2 A2 by C1 A1 plus C2 A2 into 100. Here we have to note that C1 plus C2 is always equal to 100. Similarly, C1 prime plus C2 prime is always equal to 100%. Now, next go to the linear defects or the one dimensional defects. These are also called dislocation. Now, these dislocations are one dimensional defects around which some atoms are misaligned, and these one dimensional defects or dislocations are of two types. First one is edge dislocation, in which extra or half of the plane in the solid for which the edge ends into the lattice structure. As you can see in the figure, there is plane of atom which is ended at the midway of the lattice structure, and the dislocation centers around a line called dislocation line. The second type of one dimensional dislocation or linear defects is screw dislocation, which is mainly produced due to the shear stress on the crystal. As you can see in this crystal structure, two planes are sliding over each other in such a way that the atoms of one plane and the atoms of other planes are arranged in the threads of a screw. That is why this type of defects is called linear defects or dislocation. Now, in a pure crystal, it is hard to find out any particular type of linear defects. It is always a combination of linear edge defect and screw defects. So, whenever we find a linear defect in a solid, it is always the combination of both. It can happen that one is dominating over other, but it is always the mixture of both the type of defects. As we discussed that the linear defects are of two types, and in a pure crystal it is very difficult to find a particular type of linear defects. As we said that they are of two types, that is screw dislocation and edge dislocation. And if we look at the following figure, then we can see that both the screw dislocation as well as edge dislocation is represented in the figure. Now, the extreme right hand side figure in this particular slide represents a scanning electron micrograph image of a particular solid. Here you can easily see that we do not only have the edge dislocation, we also have the screw dislocation in the scanning electron micrograph. The dislocations or linear defects which are generated due to the shear stress on the solids give a particular type of physical property which otherwise is not present in the crystal where there is no linear defects. Now, this particular property affects the electrical conductivity for a material, and if the material is a semiconductor, then we can understand the electrical property of the semiconductor on the basis of the two types of dislocation that we discussed. Most of the time in semiconductors, the dislocations give us the idea about the increase in the conductivity of the materials. And it is not only the linear defects or dislocation which gave rise to this kind of change in the electrical conductivity of semiconductor, it is also due to the point defects, because pure semiconductors are more like insulators, whereas when we dope the semiconductors with some impurity, then the conductivity of semiconductor changes drastically. And since semiconductor is the widely used materials for electronics and any kind of electronic appliance, it is very much essential to understand the concepts of defects or impurities in these semiconductor solids. Now, as we were discussing about the linear defects or dislocation, we can understand what type of dislocation or what type of linear defects are present in the solid by studying the scanning electron microscope or the transmission electron microscope data. Now, the third type of impurity or imperfection is called interfacial defects. These are basically two dimensional defects that separates two different crystallographic planes. If we think of some example of interfacial defects, then the first example which can explain interfacial defect is the boundary of a solid, because at one side of the boundary the atoms are bound with other atoms with some sort of bonding, but in the other side of the boundary it is completely free, there is no attachment with any other atoms. So, this is a type of defect which is coming under the category of interfacial defects. Another such defect is the grain boundaries that we most often observe in three dimensional solids. So, these grain boundaries are basically interfacial defects present between two crystal planes of a polycrystalline structure, because as we discussed in the case of polycrystalline materials, there are different types of orientation for the atoms in the solid that leads to the formation of polycrystalline solid. Now, if we look at minutely the interface between two crystalline phases in the polycrystalline solid, then that interface gives us a very interesting property, and those properties can be explained by using the concept of interfacial defects. Now, there are various degrees of misalignment in crystal structures between the two crystalline phases in the solid. Now, they are classified on the basis of the angle of orientation or angle of alignment of atoms in a particular phase of the polycrystalline solid with respect to the atoms in the other phase of the polycrystalline solid. Now, if the angle between the two types of atoms, or rather the atoms in one phase with respect to the atoms in the other phase is small, then it is called a small angle grain boundary, and if the angle between the two is large, then it is called a high angle grain boundary. So, you can see from this particular figure that there are two types of grain boundaries which can be explained from the following figure. As I said, small angle grain boundary and high angle grain boundary both can be seen from the figure. Now, each side of the boundary is having different phase, and each phase has different physical and or chemical properties. So, the physical or chemical properties of a solid can be explained by considering what kind of phase it has in that particular phase of the solid. So, these type of defects are called phase boundary defects, because we have two different types of phase on two sides of the boundary, and those two phases contribute differently to the physical and chemical properties. That is why they are important in the sense that the physical and chemical properties of the solid can be explained on the basis of the variation of the phase of the two types of crystallinity in the polycrystalline material. Now, if there is a mirror lattice symmetry around the or across the boundary, then such defects are called twin plane defects, and these are very interesting defects which can be studied when we study the scanning electron microscope images for a particular solid. And this is a very symmetric arrangement of atoms on both sides of the boundaries, which leads to this kind of defects in the solid. Now, to summarize whatever we discussed so far, we can present all the details in few points by giving the summary of the discussion. And if we think the major points that we discussed in this complete discussion, then the first point that comes to our mind is what are the different types of defects. As we discussed, the point defects, dislocation and interfacial defects, which are basically based on their dimensionality. Now, if we look into point defects, then we found that how to find out the quantity of point defects in the lattice, and we also went on and found the composition of different elements in a given alloy, because alloy is also a combination of atoms and impurities. Now, after that we went to the linear defects or dislocation, and we explained what are the different types of linear defects that can be observed in a solid, and the reason behind those dislocations also were discussed. And finally, we discussed the two dimensional defects or interfacial defects and the different types of interfacial defects that are found in solid, which can lead to different physical and chemical properties of solid. Hope you would have liked the lecture. Thank you.